Thank you for having me. So I'm Jordan Shivers. I'm a postdoc at U Chicago, and I'll be discussing some work that we've been doing looking at using graph neural networks with geometric information to infer rheology from structures. So essentially, the problem that we want to address is if we have detailed information about the microstructure of some material, can we predict useful things from that? Using neural networks. So the data set we're going to use is a very simple toy model of these jamming derived spring networks, where we take a network, we generate it with a certain connectivity, where Z here is the number of connections per node, and then we can deform that and measure things like the shear modulus. So I can generate a bunch of these networks, attach whatever properties of interest I'd like to learn, and then put these through a neural network. So the type of neural networks that people use for geometric graphs like this are graph neural networks. So here, by geometric graph, what I mean is it's a graph where your nodes have positions. Essentially, that's it. Your nodes also have positional information. So graph neural networks are a generalization of convolutional neural networks from essentially where convolutional neural networks apply to grids. These work on graphs, so any sort of structure. So graph neural networks, they involve these graph convolutions. So at each node, you collect information from the surrounding nodes. You repeat that a certain number of times, aggregate your information over the full graph, and then process that using a neural network. Because we're considering materials here, we want equivariance. So we essentially want our neural network to respect some symmetries. So if I'm predicting, for example, a vector quantity, I want the prediction that I get to be the same. I want the prediction that I get to rotate with my sample. Or if I'm predicting the properties of a molecule, I don't want that prediction to depend on the position of the molecule or its orientation. And this EGCL equivariant graph convolutional network architecture does this in a really simple way. So to what we refer to as a graph neural network then is a bunch of these convolutional networks stacked with an MLP afterward that we then use to predict our output. So network GNN, feed the network into the GNN, and we get some output. So how does this do? Very well. So surprisingly well. So here I'm taking a training network and applying it to 1,000 networks that it's ever seen, and just asking, can we predict the shear modulus? Does a great job. That's, it's a single scalar for an entire graph that doesn't really depend on it's not conditional on anything else. We can ask a more interesting question: can we predict the nonlinear, the stress as a function of strain? So here I'm feeding in my network and a strain value, and I'm predicting the stress of that strain. And this, again, it does really well. So this is on a sample that it's never seen. The neural network can predict, it captures this connectivity dependent behavior where you have, zero stress, that sort of stuff. Interesting thing, non-trivial things it can capture even at large strains. That's graph level stuff. So we can predict microstructural things as well. So here I'm predicting the tension on each edge given a network and a level of applied strain. So this maybe it's so yeah, okay. Well, it does a really great job. There's a lot more cool things you can do with GNNs. I'd be happy to talk to anyone about it, and I have a poster that